Math 287, Quest to College. I'm Joe Vasta, and we are covering section 6.3, Kernel and Range. So we're going to figure out what that is. What we have is we have the situation where there is a linear transformation, which is a mapping, a function from one vector space to another vector space that follows the linearity properties, the properties you always wished you can do when you first learned about functions. And that's what we covered in section 6.1. So we need some definitions of kernel and range. So let me go ahead and get this definition here. This is on your definition sheet. Let T be a linear transformation, and it goes from V to W, and that's what we have there. The set of all vectors V and V, such that T of V equals the zero vector, is called the kernel of the transformation and is denoted by ker-T. So what we have, and we'll get back to the range, what we have is we've got, this is a function that takes these vectors to these vectors. And what I've done is, it might be hard to see on the video, but the zero vector over here is blue. And then the zero vector here, I actually made it black. This zero vector maps to that zero vector if this really is a linear transformation. But you could also have other vectors that get mapped to the zero vector over here. And so what I've done is I put all those vectors, I know this is very abstract, but I put all those vectors that get mapped to the zero vector in this blue circle. So any vector that lives in this blue circle gets mapped to the zero vector through this linear transformation. And so what this blue circle is called is the kernel. And every linear transformation will have a kernel. Now let's talk about the range. The range of any linear transformation is the subset of W consisting of all transformed vectors from V. The range is denoted by RNG of T. So, like if you took each of the vectors in the domain and just start mapping them to the codomain through the linear transformation, and let's just say all these vectors are red, even the ones over here, okay, then you would start landing over here and making little red dots, okay? If we put all those little red dots together, and I put them right here, this is where all of these vectors go. They go right here, and this part that we have in the codomain, this is called the range. So we cannot have a vector in the domain that gets mapped over here, okay, because the range is this red circle here. So all these guys, everything in this red circle, or whatever that's called, gets mapped to the range. So that is what the kernel and the range is. The kernel is a collection of vectors living in the domain. The range is a collection of vectors living in the codomain. So what we're going to do is we're going to do a problem where we find the kernel. So let's do that right here. So we'll keep this picture up because the picture is pretty cool. And this picture could represent this problem right here. You have a linear transformation going from R3 to R2. Here's the matrix of the transformation right there. This is actually from 6.1 notes. So I'm using the same one because we're doing some new things. We're finding the kernel of this linear transformation. Now, if you'd like, you can rewrite this linear transformation. This is optional, you don't have to do this. As t of x, y, z equals, and it's going into R2, and I'm using this matrix to help me out, x minus y, and then this one is x minus 2z. So let's go find the kernel, because, you know, I mean, we'll see what is the kernel. It's all the vectors in R3 that when you put it through this linear transformation, it becomes 0, 0. So how do I find the kernel? Well, the kernel looks like this. It's all the vectors in R3 where you go t of that vector, it equals 0. Now this is really abstract. So remember, when we have R3 to R2, we can write t of x as a times x. So to find the kernel, we go ax equals 0. And I'll tell you where the kernel is. And this is, you know, I mean, some of you are going to go, oh, well, you're just being wise with us. But that's the kernel right there. There's the kernel. So when they say find the kernel, and you're like, I found it. No, 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 no. It's kind of like when they say find x. You don't just point to x and say, there it is. We have to figure out what this is. Okay? But here's the cool part. Ax equals 0. What does it look like this is? This is a linear system. It's homogeneous. We've done things like that before, so we'll cover up part of the picture. We have 1, -1, 0, 1, 0, -2. So what is this? I am just finding the null space of matrix A. Okay, so we'll do a row operation. I'm not going to focus too much on cranking through lots of row operations in these lectures. This one's actually not a tough step. I think what I did was go row 2 minus row 1, and that gave me the new row 2. So this is 0, 1, -2, 0. Now what I'm doing here we've done before. We found solutions to ax equals 0 many times in this class. Okay, so what we have x, y, z. X is bound, y is bound, z is free. Bound, bound, free. Which means there's going to be infinitely many solutions. Which means this kernel, when we find it, will have infinitely many vectors. Let's go find those solutions. Z is free, therefore we'll go z is t. From the second row, we have y minus 2z equals 0, or y minus 2t equals 0, y equals 2t. From the first row, we have x minus y equals 0, x equals y, so it looks like x is going to equal 2t as well. So when we solve this system, we end up getting, our solutions look like this. T, 2, 2, 1. So I went ahead and put that as an ordered triple, and then I factored the t out. So what is the kernel? Let's go ahead and officially write our answer. The kernel of our linear transformation, which is this right here, happens to be the span of 2, 2, 1. 2, 2, 1 is a basis. And so if you span that out, and that's what the span is, it's right there, but this is the official way of writing your answer. And so we're done with this problem. And here's the revelation that we should get from this. If you have a linear transformation from like Rm to Rn or R3 to R2, you'll definitely have a matrix of T. And when they ask you to find the kernel, guess what the kernel is? It is the null space of that matrix. So this is the null space of A. That is what the kernel is. Now you can plug in different things from the kernel. Watch, and like, look what's in the kernel. First of all, t equals 0 is 0, 0, 0, and if you plug 0, 0, 0 in, you get 0, 0. So 0, 0, 0 is in the kernel. You don't have to write this down. But so is 2, 2, 1. Watch, you plug that in there, it's 2 minus 2, which is 0. And then this one over here is 2 minus 2 times 1, which is 0. But this says any multiple of this, so I mean we have also in the kernel like -4, -4, -2. I mean you can check that out. -4 minus a -4, 0. And -4 minus 2 times a -2, that's -4 plus 4, 0. So all these guys are in the kernel, and there's a lot more. There's infinitely many of them. And that is why I drew my picture like this. Look, the kernel had all these vectors in them, and I kind of grouped them together. I'm like, hey, you guys, hey, kernel. I don't know if I said that, but I do know the kernel's face is all over the place. Okay, I'll continue. So I put all the kernel elements right there, and I said, you guys belong in that blue circle, and then now I know that everything in that blue circle gets transformed to that little blue dot, which in our example was 0, 0, because we were going from R3 to R2. So where does the kernel live? The kernel lives in R3, in the domain. So what do you think part B is going to be? Part B is going to ask us, with the same linear transformation, to find the range, because those were our two new definitions. Look, the title of this is called Kernel and Range. So let's go ahead and find the range. I mean, I do like this picture, so I'm going to have to, I'll bring the picture back. So same transformation. Part B, I don't want to use purple on this. It's find the range of the transformation T. Notice this one said find the kernel of the transformation, and this one says find the range. Now the range we know is going to live in R2. Okay. So how do we do this? Well, what is the range? The range happens to be all possible things that can happen. A times any vector. Now I know this is abstract, so we can say, oh, there's the range and point to it, but we're not going to get many points on the test. We actually want to find the range of this specific example. So what is matrix A? Matrix A is 1, -1, 0. 1, 0, -2. Okay, so there's matrix A. And an element from R3, well, a general element from R3 is X, Y, Z. So I'm going to go X, Y, Z. So, you know, they say, hey, what is the range? Well, the range is this, right here. There's the range. We can point to it and say, there it is. The range is also this. Okay, but it's not good enough. Okay, let's go ahead and multiply this out. We end up getting like X minus Y x minus y. And then over here we have x minus 2z. X minus 2z. Which kind of, we're not so surprised because look at that. There it is. That's kind of how you would, one way of taking the matrix of T and finding the linear transformation. That's a way of doing it. Why don't we go ahead and write this as an ordered pair? So this is x minus y, comma, x minus 2z. So there is another way of writing that. And I could put a yellow circle around there and say, oh, that's the range, but it's still not a simplified answer. What I want to do is splactor. When I splactor, I have x, y's, and z's. I'm going to have x times 1, 1 plus y times negative 1, 0 plus z times 0, negative 2. Okay, so I've splactored and now I have a linear combination of how many vectors? Of 3 vectors. Now here's the part that you'll be amazed at. Look at these 3 vectors. Those 3 vectors are the column vectors of your matrix A. So this right here is when you span your columns, you end up getting the call space of A. Is that always going to happen when they ask you to find the range going from Rm to Rn? Absolutely. So the next time we wouldn't have to write this all out. We could just remember next time that the range, Rng, of the transformation happens to be the call space. Now to write the call space, remember how you do the call space? You reduce your matrix. We kind of did the reduction there. And look at the ones that had the pivots. They were the first 2 columns. So I'm going to go ahead and circle the first 2 columns here. And so what the range happens to be, the span of those columns, because we're writing this as the span of a basis. 1, 1, negative 1, 0. And that's the way we like to write our subspaces. We like to write them as span of a basis. Does the range equal the span of these 3 vectors, 1, 1, negative 1, 0, and 0, negative 2? Yeah, but that would be like writing 3/6 for your answer instead of 1/2. Okay. Now, where do these vectors live? These vectors live in R2. They're a basis. Therefore, the span of that basis from R2 actually equals R2. So the range is R2, which happens to be the call space. Okay, so this is huge. So we've just found out that when we go to find the kernel of a linear transformation going from like R3 to R2, that the kernel is the null space of this matrix. And the range is the call space of the matrix. Some other curious things happened in this picture. The range actually equals, in the example we just did, R2, which was the codomain. So the range in this picture, so this picture, it's a general picture, but how should it look for our example? This whole codomain should be red. And so sometimes that happens when the range engulfs the whole codomain, which just means everything that gets mapped over here hit everything in the codomain. And so sometimes that happens, but lots of times this happens where the range is just inside the codomain. So we should probably take a look at a theorem here. This example holds a lot of stuff. The example that we just did here. We're going to take a look at a theorem. If you have a linear transformation going from Rn to Rm, then the kernel equals the null space, which is a subspace of Rn, and the range equals the call space, which is a subspace of Rm. Now, if I had just shown you this theorem without doing an example, most of us would have just said, okay, yeah, that's nice, whatever. But now that we did the example and worked it out, we have a little more appreciation. We understand what this means. We'll do some more examples as well. Let's go ahead and do the next theorem. I believe we should do that. This theorem right here. These are all on your definition and theorem sheet. If you have a linear transformation, this is just any general one. So notice the one in this theorem, you're going from an Rn to an Rm. Well, this is just a general one. You could be going from 2 by 2 matrices to P7. So a general linear transformation. Then, here's what the theorem says. It says the kernel is a subspace of V. And the range is a subspace of W. So basically, remember, a subspace is a vector space within a vector space. That blue thing is a subspace of V. This red thing is a subspace of the codomain. And in our example that we did, it actually equaled the codomain, which is still a subspace, because it could be itself. Okay, let's take a look at the next theorem. The general rank-nullity theorem. The general rank-nullity theorem, what does that say? It says you've got a linear transformation, and V, that's the domain, is finite dimensional. And that's what we've been dealing with in our examples. Our codomain was finite dimensional as well, but it doesn't have to be in this theorem. Then, the dimension of the kernel plus the dimension of the range equals the dimension of V. Wow, okay. So let's see what that's all about. Now this is where it would be good to be in a classroom and have this all written on the board, but we don't have that. So I'll have to go back to this piece of paper here and maybe, okay, I'm going to use a different color. The general rank-nullity theorem says we have the kernel here. You know what? Maybe not a different color. The kernel is the span of this basis. So what is the dimension of this kernel? The dimension of the kernel is 1. Okay, so let me just put that right here. Dimension of the kernel in our example is 1. Now, what is the dimension of the range of the linear transformation? Well, the range is R2, so we know that that has dimension 2. And so what the general rank-nullity theorem says, we had a rank-nullity theorem, and we'll talk about that after we just illustrate this. It says these dimensions, when you add them together, it equals the dimension of the domain, and in this case the domain was R3. And we know the dimension of R3 is 3. So the general rank-nullity theorem says this is true. 1 plus 2 equals 3. But let's dig into this a little more. 1 was the dimension of the kernel. The dimension of the kernel was how many free variables you have when you were looking for the null space. So this is really still free variables, frees, I'll say. And the range actually corresponded to the leading ones. And so that actually is the number of bound variables. So frees plus bounds equals the number of variables when you're finding the null space. But the number of variables is the number of columns of your matrix. The number of columns of your matrix correspond to R3. So remember, when you're doing a linear transformation from 3 to 2, the size of the matrix is 2 by 3. 3 being the number of columns. So the general rank nullity theorem just says dimension of kernel plus dimension of range equals dimension of the domain. But it's still saying frees plus bounds equal the number of variables of the number of columns in your matrix. So that's why it's called the general rank nullity theorem, because now you're generalizing it to linear transformations. And it's incredible. This theorem will always work, but this theorem's cool because if they ask you to find the kernel and the range and you found one of them, sometimes if you consider the general rank nullity theorem, you won't have to do much work, or you'll know the dimension of the range before you find it, and that could actually help you on some problems. So that is the general rank nullity theorem. Now we're going to continue and do some definitions here. And we're going to keep looking at this example with these definitions. The next definition. You have a linear transformation. This is a general one. T is 1 to 1. Okay, so we've seen that in a math class, so we think we know what it means. If and only if the preimage of every W in the range consists of a single vector. So if you're sitting there going, what? And then they're like, okay, let's clarify. Whenever V1 does not equal V2 in V, we have TV1 does not equal TV2. And so you're like, whoa, what does that mean? Let's go with the first one. If and only if the preimage of every W in the range consists of a single vector. So if there is a vector in the range, the thing is 1 to 1 if there's only one input going into it. So 1 to 1 is what you think it meant from the beginning. For a mapping, every input has to have exactly one output. For it to be 1 to 1, every output has to have exactly one input. And that's what this is really saying. And here's the technical way of saying it. Whenever V1 does not equal V2 in the domain, then their outputs have to be different. That's just a technical way of grabbing onto that. So T is 1 to 1 means, you know, you already have every input has one output. This says every output has one input. So it's exactly what you think about when we do 1-to-1 functions in pre-calculus or calculus. T is onto if and only if every element of W has a preimage in V. So what does this mean? If and only if every element of W, so every element of the code domain, has a preimage, which just means onto means that the range covers this thing completely. And so that's what we have. And that's what it's going to say in our next theorem, that T is onto if and only if the range, this red circle, equals the codomain, which is the big circle, which is kind of what we have in our problem. We'll move on, because they're going to have us check for 1-to-1 and onto in our examples. And so how can we do that in an efficient way? So this theorem, when you first look at it, you're probably thinking to yourself, wow, what is going on here? If I can find the theorem, oh, here it is. T is 1-to-1 if and only if the kernel equals the 0 vector. And then T is onto if the range of T equals W. And I said that's immediate from the definition. So for one thing, this theorem needs to be proved. We don't prove all theorems in here, but I'm going to dedicate this to the math majors in this class, and also other technical people who are like, yeah, why is this the case? How does that show one-to-oneness? And yes, I put an NESS at the end of that. Well, it does. Let's just assume it's true. We'll look at our example, and after we look at the example, I will do a proof of that. Okay? So we will do a proof on PowerPoint of this theorem, this part of the theorem. We don't need to do that one. So let's take a look at this. Our kernel is what we look at to see if the linear transformation is 1-to-1. And I think I'm going to need another piece of paper. Yeah. Let's use another piece of paper. So this is still problem number 1. Our kernel of T does not equal just the 0 vector. Sure, 0, 0, 0 does live in the kernel, but the kernel is not just the 0 vector, it's actually infinitely many vectors. Therefore, you don't have to use this fancy notation. Therefore, there's 3 dots, and that means therefore in math. Not there 3. So therefore, T is not, and then we sort of do shorthand for 1-to-1. 1-to-1. So we look at the kernel to see if a linear transformation is 1-to-1. To see if a linear transformation is onto, we look at the range. Okay, so notice the range of T, we saw that that equals R2, which if you look back at the original problem here, that right there is our codomain. This is the codomain. And we could say of T if you'd like. Those guys are equal. Therefore, T is onto. Okay. We might be done with this example. Before I get into the proof of that theorem, let's take a look at my favorite picture here. So, when this kernel is just that dot, so when the kernel goes whoosh, then this thing is 1-to-1. When the range, you know, think of this as paint coming over here, and every time you send something over, you put a little red dot of paint. So let's suppose you sent them all at the same time, and the range just goes, it covers the codomain, then it's onto. So 1-to-1, onto. Let me go ahead and write out this, because you're like, well, what do I write for that? What is and those are my sounds for 1-to-1 and onto. Now, let's just write this out. It's 1-to-1. This thing is 1-to-1 when the blue part is just a dot. And the dot it would be the zero vector, because zero vector has to go to zero vector. A linear transformation is onto when W, which is the codomain, is all red. Okay? And the more examples we do, the better. So what we're going to do now before we hit example 2 is we are going to do a PowerPoint derivation of t is 1 to 1 if and only if the kernel of t equals the zero vector. Okay, so let's go ahead and show our theorem. You've got a linear transformation from v to w. The theorem says t is 1 to 1 if and only if, that's that double arrow there, the kernel of t equals the zero vector. Okay, so when you prove an if and only if theorem, you've got to prove it both ways. You have to prove, this is the one I'm proving first, if t is 1 to 1. So we're going to assume that's true, and then we're going to prove this, that the kernel of t equals the zero vector. And then you've got to prove it the other way. So let's prove it this first way, okay? So we have that arrow that shows we're proving it that way, and we assume, or suppose, t is 1 to 1. Well, saying that a linear transformation is 1 to 1 says that, like, if you try to do the linear transformation of some vector and it gives you the zero vector, that right there can only have one solution. Okay, that's the whole idea of 1 to 1. Okay. Well, that vector up here has to be the zero vector, since we have a property of linear transformations that says the zero vector from V has to get mapped to the zero vector from W. Okay, so T of V can only have one solution. That means the kernel can only have one element in it, and the element has to be the zero vector. Therefore, and there's those 3 dots there, the kernel equals the zero vector. Let's go ahead and do the proof the other way. We're going to start off with suppose this. So we're going to suppose this, and we're going to show that t is 1 to 1. Suppose that the kernel equals the zero vector. And now we're throwing this in. T of u equals t of v. To show 1 to 1-ness, I'm going to, because this is general, I'm going to kind of use logic and the math to get to the fact that if t of u equals t of v, so we think they're different, but if we're trying to show 1 to 1, we're going to show that u equals v. And that actually is the clever way, the technical way of showing 1 to 1 in some cases. So what I'm going to get is, well, I want to point out that u and v have to be vectors in the domain vector space V. And since they're vectors, I could consider the vector u minus v and send that through the linear transformation, and that's what I'm going to do. So I consider the vector u minus v, send it through the linear transformation. Now, because it is a linear transformation and you can do all those things you dreamed about with functions, this is written as t of u minus t of v. It's the linearity properties. So t of u minus t of v, but then since t of u equals t of v, that is actually going to be the zero vector. And so this is, since t is a linear transformation, that's the first equal part. And then because it equals 0, that's because of our assumption there. So what does that mean? If u minus v gets mapped to the zero vector, then u minus v must be in the kernel of the linear transformation. That's the definition of the kernel. And if u minus v is in the kernel of the linear transformation, then u minus v has to be 0. Why? Because of our assumption up here that the kernel is only one element, the zero vector. So that u minus v has to be the zero vector. And now we just use the properties of an equation and say that u equals V, and that shows, then I say we were going to do that. That shows 1 to 1. Therefore, and there's those 3 dots again, T is 1 to 1, and we've shown this theorem, which is huge. Why is it huge? Because it makes verifying whether a linear transformation is 1 to 1, it makes it a lot simpler. So now we're going to go back and do more examples. So back to my favorite picture here for this section is we've got all this stuff that shows what the kernel and the range is, and we've got these neat noises. The linear transformation is 1 to 1 when the kernel goes, and the linear transformation is onto when the range goes, just covers it all up. And so I think this stuff is pretty cool. It's abstract, and so you're thinking to yourself, what a waste of time. But a lot of stuff that we do is built onto this theory. It looks very theoretical, but we'll be solving differential equations, and those differential equations, we're going to be considering kernels of linear transformations. And I know it sounds like I'm just making that up, and maybe I am, but you'll see. Just hang around in this class and you'll see this stuff applied to differential equations, and you'll see differential equations play into circuits, oscillations, mixing problems, etc. So now here's a whole slew of things that we want to find out from this linear transformation. It's a new example. Find the kernel and its dimension. Find the range and its dimension. Is this linear transformation 1 to 1? Is it onto? And verify the general rank-nullity theorem. That one usually verifies like 3 plus 1 equals 4 or something like that. So that one's always fun to do. So what are we going to do with this? The first thing that I'm going to do is when they give me a matrix like this is to do some row operations. So that's what I'm going to do. So my row operations, when I did them all, it doesn't take too much time to get to this. I got 1, 1, 0, 1, 0, 0. Okay? Now I know I didn't start off the last problem like this because I didn't know all those theorems. Now I do. Because now when I'm asked to find the kernel of a transformation, what I'm really finding is, for this example, the null space of A. That's what I'm finding. Now let's take a look at A. Here's X, here's Y. To find the null space of A, I'm going to do this more often in this class, and it might make some of you feel uncomfortable, but oh well. I'm going to say the augmented matrix would just have zeros on that last column if I actually, put in another column of zeros. And that's how you find the null space. So there would be a 0 here, a 0 there, and a 0 there. And I'm usually going to do it in red. Well, let's look at our variables. Look what we have. We have bound, bound. Both of my variables are bound. In fact, if you read out off the second row, it says y equals, and then that red thing is a 0. So y equals 0, and then look at the first row. It says x plus y equals 0, x plus 0 equals 0. X is 0, y is 0. Null space is what? Null space is 0, 0. So we've just found the kernel of the linear transformation. It is 0, 0. Now, what is the dimension of that subspace, or that vector space within a vector space? See, the kernel does live in R2, doesn't it? There's only one thing. It's 0, 0. The dimension is actually 0. Now, I might do these a little out of order. The kernel tells you about which one here, 1 to 1 or onto. It tells you about 1 to 1. And the theorem said that you could see it is one-to-one if and only if the kernel equals the 0 vector. Does it equal the 0 vector? And the answer is yes. So guess what? This linear transformation is one-to-one, which maybe means we could use it in cryptography. Or maybe not. Maybe we have to know something about ontness. Here are some things that I do not want you writing down. Okay? So on the exam, so let's say you're taking the exam and you go, oh, I just found the kernel. Does this red pen work? Yes. And then you say, there it is. This is not specific enough. Yes, it's correct. The kernel in this case is the 0 vector. But since we are talking about more than one vector space, we can't just say, oh, it's the 0 vector, because I don't know if you know which 0 vector it is. So when you write this out, even though this is kind of close to what you want to put, this is still a little too general. So this is the first thing that I do not want to see that on the exam on a problem like this, because I want to know exactly the 0 vector. Here's something else I do not want to see. I do not want to see span of 0, 0. Now technically, you're just taking all linear combinations of 0, 0, which is just 0, 0. So technically this does equal this. But this guy right here is not simplified. Because if the span of 0, 0 is just 0, 0, then 0, 0 is the simplified form of that. Okay, so I see that a lot on exams, and I see just putting, let's just put the 0 vector, and then the teacher could decide like which 0 vector I met. And maybe I met the 0 vector of 2 by 2 matrices, and ha ha ha, you don't know because I just put this. So make sure you're very specific. And that's one thing that I wanted to say for exams. Let's go ahead and, we've already done a few of these. Look, kernel, its dimension. It's one-to-one, yes. So now let's go ahead and figure out the range. The range of our linear transformation happens to be the call space of A. And we want to write our call space as the span of a basis. Well, how do you find the call space? You reduce your matrix, and you look at the columns that have the leading ones, and then you go back and take the original columns. So the call space is going to be the span of 1, 2, 1, and 1, 3, 3. So there's the range. Okay. Do the span of both of those vectors, does that generate all of R3? Well, no. How many vectors do you need to span R3? You would need 3 vectors because the dimension is 3. What is the dimension of the range? Well, count your basis elements. The dimension is 2. So let's check for ontness. Ontness says, well, this is either going to equal the codomain or it doesn't. So does it equal R3? We've already talked about it. No, it doesn't. It does not equal the codomain. Therefore, guess what? This linear transformation is not onto. Okay, so we've done almost everything except verifying the general rank-nullity theorem. The general rank-nullity theorem says the dimension of the kernel, 0, plus the dimension of the range 2 equals what? Well, you can tell me what 0 plus 2 equals. It equals 2. But where did this 2 come from? This is, let me color code this, the dimension of the domain. So that, color codes with that. My orange cap was off. This right here, color codes with this one. And this one we'll make in blue. Is that one right there. Dimension of kernel plus dimension of range equals the dimension of the domain. I know those are a lot of words, new vocabularies, but really what it says is there's 0 free variables, plus 2 bound variables equal the number of variables. And the number of variables you get from the columns, and the columns line up to the dimension of this first one. So this completes problem number 2. Let's move on to another problem. Oh, before we move on to the other problem, I go back to my favorite picture. What just happened here? This one is 1-to-1, but it's not onto. So the right-hand side looks like that, where the range is less than the codomain. It's not covering the whole thing up. But the left-hand side, it is 1-to-1, which means the kernel is like, and it's just a dot. The kernel is just a dot in my diagram. I know you're like, stop showing me the diagram. Well, there it is. What would be funny is if, like, you got so sick of this diagram and then, like, I emailed you guys all with an attachment. Very important document about your status in the class, and then you opened it up, and then it was, all it was this, like with haha or whatever. That would be cool. I do know there's at least one person in here, besides me, I mean one person in the class, one student in the class, who really likes this diagram. It's really cool. Okay, let's go ahead and do another problem. Problem number 3. It's going to ask for the same stuff. So I didn't write it all down out of laziness, but it's asking for the kernel, its dimension, the range, its dimension. Is this linear transformation 1-to-1? Is it onto? And then we'll verify the general rank-nullity theorem. So let's get going with this. This matrix gets reduced to 1, 3, 0, 1. Okay. So the first thing we're going to do is find the kernel. The kernel of this equals the null space of A. What is the null space of A? The null space is when you solve the homogeneous linear system. So there's zeros there. This right here is X. This is Y. Look at your variables. Leading one there, leading one there. Your variables are both bound. Bound, bound. And so Y equals 0, X equals 0, the null space, or the kernel, which is the same thing in these examples, the kernel actually equals 0, 0. So it's the same answer as the last problem. That's all right. Okay, so there it is. What is the dimension of the kernel? Well, it is 0. What does this tell me about either onto or 1-to-1? It tells me that this linear transformation is 1-to-1. Let's go find the range. The range of the linear transformation is the call space of the matrix. The call space, to find that, you want to write that as a span of a basis. Well, you look at the leading ones and pick up the original columns. And some of you are about to say something, but I'm going to write this down anyway. This is the span of 1, negative 1, 3, comma 1, because those columns corresponded to the leading ones. But you're spanning two things. This is a basis in R2, and there's two of them. So what we have is a basis for R2. This actually equals R2. So there's the range. The range is R2. The kernel is 0 vector. What's the dimension of R2? Dimension of R2 is 2. Does this equal, does the range equal the codomain? Now when I'm pointing to this. This is the codomain, not this. And you're like, but it's the same thing, but I will always just point to this one. So does R2 equal R2, which is the codomain? And the answer is yes, which makes this linear transformation onto. So this is both 1-to-1 and onto. Now this is what I would use for cryptography. Okay, I would like onto and 1-to-1 if I was doing cryptography. So verify the general rank-nullity theorem. Well, the general rank-nullity theorem says the kernel, the dimension of the kernel, which is 0, plus the dimension of the range, which is 2, equals the dimension of the domain, which is 2. Let's identify where these came from, because that's an important thing to do as well. This 2 came from not that, it came from this right here. And then this right here is the dimension of the range, and then the 0 is the dimension of the kernel. Now, before we move on, let's go ahead and take a look at this last theorem from 6.3. You've got a linear transformation. Let V and W be finite dimensional, so they both have to be finite dimensional here. And it says T is 1-to-1. If T is 1-to-1, I'm sorry, then the dimension of V has to be less than or equal to dimension of W. Now, is this going to help you when you're doing your problems? Not necessarily. This is just some theory that we're throwing at you. So we've got some examples where the dimension of V is less than or equal to the dimension of W, and that's right here. So this was the case, and it says if T is 1-to-1, then that will happen. And we had T is 1-to-1, and it happened. Doesn't mean it's the other way around. The converse is not necessarily true. We can't say if this happens, then T is 1-to-1. So we got to be careful with our if-then statements. If T is onto, then it's the other way around. Then the dimension of the domain is greater than or equal to the dimension of the range. That was the setup in problem 1, and we ended up finding out in problem 1 that it was onto. We'll see some cases where the converse is not true on these, okay? So just know that we will. If T is both 1-to-1 and onto, so that's what we have in the last example that we just did. And I can't believe I've already, I said I've misplaced it. It's hiding under this sheet here. If they are both 1-to-1 and onto, then the dimensions of those vector spaces, the domain and the codomain, have to be equal. And that's what we have. We had both 1-to-1 and onto, then those dimensions must be equal. Now the converse is not necessarily true, but we're going to try to get something that looks a little like the converse. If the dimension of the domain equals the dimension of the codomain, then T is 1 to 1 if and only if T is onto. So what does that really mean? It just means if these dimensions are the same, then you'll have one of two things with 1 to 1 onto. You'll have them both be 1 to 1 and onto, or you'll have not 1 to 1, not onto. That is what this means. So when they ask 1 to 1 and onto and the dimensions are the same, it will either be yes, yes, or no, no. That is what Theorem 4. So Theorem 4 was trying to be the converse of Theorem 3, but the converse is not true. So to try a little harder, we did it this way, and then we're like, we're good to go. Okay, so once again, if you know how to do the problems, and this stuff, it's kind of fuzzy, or you don't remember it. It's the problems. Doing your homework problems is the key. So we're going to move on to problem number 4, and problem number 4 is going to involve problems 1, 2, and 3. So I know some of you are going to say, what are you doing to us here? So you'll see. Find out where, okay, definition. Here it is. I'm throwing you some definitions from the next section. And it says, if T is both 1 to 1 and onto, so that's what we had in the last example, then the inverse transformation. So there's a transformation that you can take back the other way. Then that's defined by T inverse W equals V if and only if W equals T of V. So it just takes things back. That's all that says. But in order for the inverse transformation to exist, for it to be defined, you got to have your original transformation. It has to be 1 to 1 and onto. So let's take a look at the next theorem. The next theorem says this. Let T be a transformation that goes from Rn to Rn with the matrix A. T inverse, that's what we're talking about up here, exists if and only if the determinant does not equal 0. And look what we have up here. The determinant does not equal 0. If the determinant did equal 0, it would be a non-invertible matrix, which would have then given us a free variable, which would have ruined this, which would have said, no, it's not 1 to 1. T inverse is a linear transformation. And guess how you get that linear transformation? You just take the inverse of matrix A. So that's how you find the inverse linear transform. So what do you think? You know what? That's what they're going to ask us. I might as well do it right now in 6.3 because we have nice examples. I used to do this completely separate and it was very inefficient. So let's go ahead, take a look at some examples. Here are the examples here. 1, 2, and 3. Find the inverse linear transform. Did I say transform? I keep saying transform. I'm going to say transformation. So that's what we're doing. Find the inverse linear transformation of examples 1, 2, and 3. Now, we could look at that theorem and say, oh, well, T has to be both 1 to 1 and onto, so we could already say, no, 1 doesn't have 1 and 2 doesn't have 1. But suppose we forgot that and we're like, okay, let's go find the inverse matrix here. Well, you can't find the inverse matrix of a non-square matrix. So those guys, we're just going to throw in the trash, kind of. I mean, we'll write them out. Okay, so for number 1, find the inverse linear transformation. Okay, so I got to remember to say transformation. Problem number 1, its DNE does not exist. Problem 2, guess what? It wasn't onto for problem 2, so this one is also DNE. But for problem number 3, it was both 1 to 1 and onto, and so to find the inverse linear transformation, I just have to find A inverse. Okay, so A inverse is 1 over determinant. Determinant is 4. Now notice if the determinant had been 0, then I wouldn't be able to find this. I would have ended up getting no and no for those. 1/4. I switch my DNA. on that matrix, which doesn't look like I did anything at all, but I switched it really. And then I'm going to negate my B and C. Minus B minus C. So my matrix of transformation for the inverse transform looks like this. Looks like 1/4 minus 3/4, 1/4, 1/4. And what does that mean? Well, let's take a look at writing this out. I'm going to write it out like this. I'm going to say T inverse of xy equals, and then look at the first row here. So it's going to be 1/4 x minus 3/4 y, comma, and the next one's going to be 1/4 x plus 1/4 y. Okay, so we found the inverse transform here. Now we could say, hey, let's just take a look at a vector. So we're done with this problem, by the way, and now we're just having a little fun. And some of you are like, well, I don't think this is very fun, but anyway, we'll just pretend like you're having fun. Let's just take a vector 2, 3. I have 1, 3, negative 1, 1, and I send it through the transformation. So by putting the 2, 3 here, and this gives me 2 plus 9 is 11, and the other one is negative 2 plus 3 is 1. So what happened is we went ahead and sent 2, 3 lives over here in the domain, and it went to the range. Now the inverse transformation takes it back to the domain, and it should take it back exactly where it came from. So let's see if we can do that. So that would be 2. I'm just looking at something here. Plus 1 is 12, 3. Okay, so I'm actually just going to use this matrix right here to do that. 1/4. And we know it's going to do that because we've done inverse matrices before. But it's kind of neat because now we're thinking of linear transformations, and then we go 11, 1. And what do we have here? We have 11 minus 3 is 8. And then 11 plus 1 is 12. But of course, what did I forget to put? I forgot to put 1/4, and I'll put it over on that side because I can't fit it over there. 1/4 times 8 is 2. And 1/4 times 12 is 3. So we've just sent that vector 11, 1 back. And this is really applicable to cryptography because when you encrypt something, the hope is that you can decrypt it. And so sometimes you'll use linear transformations. Let's continue. Now things are going to get a little weird. And you're like, things already got weird, Joe. Okay, so we have like 3 more problems to do. Now, looking at problem 5, my linear transformation's going from P3 to P2. And sometimes the book will say P3 of R, P2 of R, but you know, when I don't have it, it just means the coefficients are real. And the linear transformation looks like this. And you can see it's taking a general polynomial from P3. P3 is polynomials of degree 3 or less. So A could be 0 there, and you would still be in P3. And it takes me to a polynomial that says something x squared plus something x plus something. So that's the linear transformation. What are the directions here? The directions are to find all that stuff. The kernel, its dimension. The range, its dimension. Is it 1-to-1? Is it onto? Verify the general rank-nullity theorem. So we're going to do all that stuff. So I'm going to start off with the kernel. The kernel of the transformation. So how do I find the kernel of a transformation? I say T of x equals 0. Now you might go, well, Joe, don't you find the kernel by finding the null space. The null space of what? I don't see any matrices there. We have not defined a matrix of transformation for other weird vector spaces. We've only defined a matrix of transformation from Rn to Rm. So now we're just back to this where I circle this and say, well, there's the kernel. What is T of x? Or T of this? It is this thing right here. So I'm going to set this thing equal to the 0 vector of P2. And what is the 0 vector of P2? It's the polynomial y equals 0 or just 0. So that's what I'm going to do. So a plus b minus c plus 2d x squared. So all I'm doing is copying that down. This is a plus b plus d x, and then we have plus c minus d equals 0. Okay, so I'm trying to find the kernel. I could have said t of this equals 0, and then t of this really is this. So I'm setting this thing equal to 0 to try to find the kernel. Now what I'm going to do is, in order for this equation to be legitimate, the coefficient in front of this x squared here, a plus b minus c plus 2d, has to equal the coefficient of that x squared, which is just 0. So what I have is I have a plus b minus c plus 2d must be 0. And then I also have that this guy, the coefficient in front of this x, has to be 0 because there's a 0x over there. So I'm going to write that below. This is going to say a plus b plus d equals 0. And this guy right here, this is the constant, c minus d, that has to equal 0 as well. So c minus d equals 0. Okay, so look what I have here. I have a system of equations. So what am I going to do with this system of equations? I'm going to go ahead and write it into a matrix. Now before I write it into a matrix, okay, so you want me to write the augmented matrix? I'm just going to write the coefficient matrix, and I'm doing this on purpose. The coefficient matrix is 1, 1, negative 1, 1, and I'm not going to put the zeros. So 1, 1, negative 1, and I can see where I messed up because I see a 2 here, and somehow the 2 didn't get copied down there. So I don't know if I've got all this paper around here. I'm going to just try to move that D over and then put the 2 there. Oh, I hate copy errors. I hate when you do a copy error and you don't catch it, and then you're wondering what just happened, but I remembered the 2 and then I didn't see it, so I was a little suspicious. And then over here on this equation, I'm just looking at the coefficients. I'm not putting the 0 there. I have 1, 1, 0, 1. And then over for the last one, it's 0, 0, 1, negative 1. For some reason, this is going to be very important. Okay, now I'm trying to find the null space, so there's some zeros there, and I'm not going to put them there on purpose. Now watch this. This row here came about by setting the coefficient on the x squared to 0. So this row came about by the x squared. And this row, 1, 1, 0, 1, that's this right here. This corresponds to those letters. So there's an x there. And then this row corresponds to the c minus d. So that's just a 1. Now let's look at things a little differently here. This is x cubed right here. This column corresponds to x cubed. Now, you would say, well, where are you getting that from? Because doesn't this column, isn't it represent A? Yeah, it does. But what is A in front of? I'm actually trying to find this right here, the kernel. And the A is the coefficient in front of the x cubed. And this column corresponds to B, which is the coefficient in front of the x squared. This column corresponds to C, you can see that, which is the coefficient of x. And this column corresponds to D, which is the coefficient of 1. So this matrix is kind of unique because, remember we said there wasn't a matrix of T for things that weren't going from Rn to Rm. But watch this. This guy here has dimension what? Dimension 4. And this guy over here has dimension 3. Look at the size of this matrix right here. It's not 4 by 3, but it's what? 3 by 4. So this matrix seems kind of important. We are actually finding what on this matrix? The null space of the matrix. Isn't that what we were trying to find on a matrix on the other problems that involved Rn and Rm? We try to find the null space of a matrix. So let's continue this problem by simplifying that matrix. When I simplify that matrix, okay, so I'm going to get this right here. I know I'm going to have to go off on another piece of paper pretty soon. 1, 1, negative 1, 2. Okay, so that's not very surprising. And then we have 0, 0, 1, negative 1. That looks like row 3. And then this one's going to be 0, 0, 0, 0. So that's what I got when I did some row operations. And what am I trying to find? I'm actually trying to find the null space of that matrix, so I'm going to put some zeros here. And I know my variables, let me go ahead and label the variables as A, B, C, D. Okay, even though they kind of correspond to that. I think I'm going to need some more paper here. Well, pretty soon. Okay. So look what I have. Let me circle all the leading ones there. Those variables are bound. So we have bound, and then B is free, C is bound, D is free. So when you go to solve this, those red dots are zeros. I end up getting D is T, because he's free. The second row gives me C minus D equals 0, so C equals T as well. And then B is free, so B equals S. And then the last thing that I'm going to say here on this, finding this, is A plus S, I'm doing the first row, minus T plus 2T equals 0. So what does A equal? A equals, what? A would equal negative S minus T. Okay, so let's move on here. So I'm trying to find the kernel here, and somehow it's boiled down to trying to figure out what A, B, and C could be in order to make it 0. Okay? So this null space looks like this. It looks like minus S minus T, comma, S, comma, T, comma, T. I'm going to splactor. And when I do that, I have S, this is negative 1, 1, 0, 0, plus T, which is negative 1, 0, 1, 1. So what did I find? Let's call this matrix here A. I found the null space of A. Now, is that going to be the kernel? No, it's not going to be the kernel of this one. It would be if we were going from R4 to R3, but it's not. Let's write out the null space anyway, even though it wasn't asked for. The null space of this matrix is the span of what? These two vectors. So let me write that down. This is -1, 1, 0, 0. And then the other one is -1, 0, 1, 1. Now what else did we find? Well, actually, let's not start talking about the range yet. So the null space is that. But what do we really have here? We were trying to find all the polynomials that would get mapped to 0. And those polynomials would be corresponding to something with this, with the A's, B's, C's, and D's. Okay. So this first coordinate is an A, that's a B, that's a C, that's a D. So that would make this kind of polynomial look like this. It would look like x cubed plus x squared, and then plus 0. So this is kind of telling me that this is x cubed, or negative x cubed, because there's a -1, plus x squared. So just remember this, there's 4 of them here, and it kind of lines up with these. I'm going to put an x cubed here, an x squared, an x, and a 1. And then on this one, it's the same thing. This is x cubed, x squared, x, and 1. So what we're trying to find is the kernel, and the kernel doesn't live in R4. Our kernel lives where? In P3. And so that's what we're going to find, and it's going to line up right with the null space of that matrix. So the kernel of T equals the span of, and instead of writing this as an element in R4, look what I'm going to do. I'm going to write it as an element in P3, which is negative x cubed plus x squared. That's the first element. And the second element here is what? Negative x cubed plus x plus 1. There's the kernel. I know that took a long time to get to, but just think about it. I mean, remember, if you don't like me putting x cubed, x squared, x, and 1, you can think this is A, this is B, this is C, this is D, and we're trying to look for these creatures that get mapped to 0. Well, that's when A is -1 and B is 1. And when you have that, it ends up giving us this. And then this is A is -1, B is 0, C is 1, and D is 1. And if you put it into these kind of creatures, because that's what the kernel is, it's that thing right there, then you end up getting exactly that polynomial. But the thing is, the reason I do it this way is because you are actually finding the null space of a matrix. Now this matrix, we haven't defined what it is. There's going to be a name to this, but right now we are able to do this. So if the null space can yield the kernel, so the null space does not equal the kernel in this example, because those are not Rm and Rn, but it can yield it pretty simply, then the call space can yield the range. And we'll talk about one-to-one and onto after that. So let's go ahead and find the call space. I'm going to write the call space of matrix A is, now I think I should probably go like this. Oh, this is going to be hard to fit all this. Let's put this under like that. So here's matrix A. The call space is going to be the span of, okay, I take my leading ones, and I don't grab those columns, I go back to the original matrix and grab the columns corresponding to those those leading ones, which would be column 1 and column 3. So when I do that, column 1 up here is 1, 1, 0. And column 3 is negative 1, 0, 1. So that's the call space. Now that's not what was asked for, but that is going to have a connection to the range of our transformation. The range of the transformation. So now remember, look at these columns. These columns look like what? X squared plus x for that first column. Look, x squared, you could put that thing right above if you want. X and 1, so x squared plus x plus 0 times 1. So the range is not going to be elements from R3, it's going to be elements from P2. So the range equals the span of, and then we go look at this. We have x squared plus x. And then over here, this is going to correspond, here's an x squared, here's an x, and here's a 1. So this one's going to be negative x squared plus 1. Okay, now I'd like to make this connection because I think it's great. Now the book doesn't really want to make the connection. Sometimes they'll just say solve for A, B, and C, and D when you're finding the kernel, and then try to piece it together and look up here and see what the kernel is. But I like this connection because I can write down null space and it gives me a really good roadmap to writing out the kernel. And I can find the call space and it gives me a really good map. Now your book for the range, they're going to say you write this out and then use splactor. They're not going to use the word splactor. And then you'll have a linear combination of something times A plus B times another vector plus C times another vector plus D times another vector. Now the deal is with that way, sometimes you might get a collection of vectors where there's some dead weight and then you would have to take care of the dead weight. But with this method here, where you look at this matrix, find the call space of this matrix or a basis for it, you know that your answer is going to be a nice span of a basis. So that is the deal. You stick any one of these two polynomials into the linear transformations of the polynomials from the kernel. You stick, like, negative x cubed plus x squared into this, you will end up getting a 0. You can verify that if you want. And you stick this polynomial in there, so A is negative 1 and C is 1 and D is 1. By the time you're done computing this, it will all be 0. But here's the cool part about this. If you take any linear combination of these two polynomials and write out that polynomial and then put it in this linear transformation, guess what? It equals 0. The range just tells us like all the polynomials that come out of the linear transformation. So you can plug all polynomials in there. Any polynomial that comes out the other side is going to be a linear combination of those two polynomials. So that's what the range is. Let's go ahead and answer some other questions. We will do another problem like this, and it will involve matrices for the vector spaces. I'm going to make sure the camera hasn't stopped. The battery is blinking, so it is low. So I don't know if I'll even be able to get through this example. Let's look at the dimension of the kernel. What is the dimension of the kernel? It is 2. So dim equals 2. What is the dimension of the range? Well, it is also 2. Dim equals 2. Let's verify the general rank-nullity theorem. General rank-nullity theorem, which says what? 2 plus 2 equals 4. And what is 4? 4 is that dimension right there. So I believe I was color coding this. Here's dimension 4. It equals that. And where's the brown pen? This 2 is that one right there. And this 2 is that one right there. So the general rank nullity theorem still works, will always work. Let's talk about one-to-one and onto. Kernel tells us about one-to-one. Does the kernel equal the zero vector from the domain? Is that the zero vector? No. So this is not one-to-one. Onto. Does the range equal the codomain, which is P3? The codomain is not P3. The codomain is P2. Sorry. So does the range equal the codomain, which is P2? Well, P2 has dimension what? This has dimension 3, doesn't it? And that has dimension 2. So, no, it doesn't. That would tell you this linear transformation is not onto. And so we end up getting a no here, but that doesn't have anything to do with the theorem with the same dimensions. These dimensions were different, so anything can happen. And that pretty much finishes up this problem. There's a few more things I want to say about this problem that will help us understand something else. So remember, in this problem we have this green matrix, which was supposed to be kind of important. Okay, so we have this green matrix which sort of describes what's happening with this linear transformation. Okay, so I need another piece of paper. What this green matrix is, so we're done answering all the questions, but now we're kind of defining something. This green matrix happens to be this right here. So it's a matrix, and this column is T of x3. Well, is it? Well, what is T of x3? If you just put x3 or x cubed into there, so a is 1 and all the other ones are 0, then what do you end up getting? This gets you what? X squared plus x. So this is x squared plus x. But really what I want is the component vector with respect to a basis c. So instead of saying x squared plus x, it's going to give me 1, 1. And that's, remember, component vectors. With respect to this ordered basis, x squared, x, 1, which is a basis, an ordered basis for P2. So notice this is an ordered basis for P2. Up here, x cubed, x squared, x1 is an ordered basis for P3. So you can verify that T of x3, the component vector, it really is 1, 1, 0. So the next column is actually T of x squared. And you can see the x squared there. And then we go and take the component vector. So let's see how that works. T of x squared, that's where b is 1 and all the other ones are 0. And so you end up getting x squared plus x plus 0. So 1x squared plus 1x plus 0, the component vector would then just be 1, 1, 0. And so that's what that gives. So not that you're going to be writing this out in your homework, but I'm just kind of showing you this example. So the third column is going to be, we'll take a guess, T of x, and then you do it relative to the basis c, and then look. So that's if you've got x. Okay, so x has a 1 there, a 1 for c, and then a, b, and d are 0. So you end up getting negative x squared plus 1. Negative x, so negative 1x squared plus 0x plus 1 times 1, and there's the component vector. And then the last one is this one right here, T of 1. And then we take its component vector. And that's really what this matrix is. So this matrix has notation, and we don't want to get caught too much in this notation, but there's a few problems that later in the chapter that will have this. And there's the notation for that. So we've been calling it A just because we didn't want to overwhelm you. We're done with the problem in terms of finding the domain and range and all that stuff, but that's what that vector's called. So it has a name. It's called the matrix of T. So it really is a matrix of transformation, but then you have to say something else because we're not going from Rm to Rn. It's the matrix of T relative to bases, to ordered bases, B and C. That's what it's called. So I'll put up the ordered bases here. Ordered bases B happens to be an ordered basis from P3, which you can actually find just by going along the columns. It's x. So it's ordered, so x cubed, x squared, x, and 1. So this is x cubed, x squared, x, and 1. And then here's ordered basis C from P2, which you just follow this down right here. So this is x squared, x, and 1. X squared, x, and 1. Okay, so this matrix of T relative to ordered bases B and C. And sometimes they may write the ordered bases in a different order, or sometimes if you had done this differently, well, it all depends on the transformation they give you. They might have put the constant first and then the x and then the x squared. So we'll do another example, but what I'm covering now is stuff from 6.5. So this is 6.5. So you're wondering why section 6.3 is so long. Well, we don't want to discuss that. We're done with problem 5. We'll do another problem that's similar to that. And now we know all the definitions. But before we do that, let's go ahead and take us to a problem that's probably pretty simple compared to the last problem. It's this right here. You have a linear transformation from V to W. And I give you the dimension of V, which is the domain. I give you the dimension of W, which is the codomain, so we have 7 and 11, and then the dimension of the kernel is 3. What is the dimension of the range? So this is actually a pretty simple problem. If you remember the general rank-nullity theorem, it says the dimension of the kernel plus the dimension of the range equals which one? So you got to remember, which one does it equal? It equals the dimension of the domain. So this one has to be 4. Now let's take a look at our picture. Here is, I'll try to reproduce the picture I had on the other page. I just want to have a new picture for this problem. So we have V, and then we also have W, and then we have the 0 vector there, which I'll make in blue. Okay. And this part's the kernel, and this part's the range. I try to keep the same colors. What is happening here, so we're done with this problem, is that the kernel has dimension 3. I'm going to put 3 there. The dimension is kind of the size, sort of. Okay. But the dimension of V happens to be bigger than 3, isn't it? The dimension of V is 7. So you know what I'm going to do, and this will make some mathematicians feel a little uncomfortable. I'm going to put a 4 out here. Now, that disk does not make a vector space. For one thing, it doesn't have the 0 vector. But I'm just going to say, okay, the size of that thing is or the dimension of the outside area is 4, and then they add up to 7. Okay? At least this makes sense to me. Now, the dimension of the range we got was 4. What is happening? And this might remind you of some string theory or some weird stuff they do in physics. What happened is our universe had 7 dimensions. We have the kernel here. After it got sent through the big crunch or whatever, that kernel collapsed into one little point, a 0-dimensional point. And then the rest of the dimensions spread out and became the range. So 3 dimensions get mapped into 0 dimensions, and then the 4 dimensions out here get mapped into the range. I just think that's really cool. Maybe you don't. So let's go ahead and do the last problem. The last problem, I have the instructions here. It takes like half the paper to say the instructions. We are going from P3 to M2, so this is really weird now. Here's an element from P3, and look, it's written the other way. You know, here's the constant, and here's the x cubed, but we'll deal with that. And then here is the linear transformation. M2 is 2 by 2 matrices. I'm giving you some ordered bases, and they kind of like, it says 1x, x squared, x cubed. It kind of goes in the order of which we see them, so that's a good thing. And then E11, E12, E21, E22. I mean, that's how we really want to see an ordered basis for 2 by 2 matrices. What are we trying to find in this example? This is our last example, so some of you have already fallen asleep, so let me say, wake up, wake up! This is our last example, and this is probably one of our longest YouTube videos. We're trying to find everything. We're trying to find this matrix, which we call the matrix of T, relative to the ordered bases B and C. Now I know that sounds like really bad, okay? We'll write it down. But that's going to help us find the kernel, the range, the dimensions. Is it 1-to-1? Is it onto the general rank-nullity theorem and T inverse? So let's go ahead and do this. One thing to maybe start off with is tracking these dimensions here. The dimension of P3 is 4, and the dimension of M2 is also 4. Now, if you remember some theorems, if those dimensions are the same, then for 1-to-1 and onto, you're either going to get yes, yes, or you're going to get no, no. Now, if you're like, no, I don't remember that theorem, Joe. I kind of dozed off on that part of the video. That's all right. Let's just go ahead and do this problem. How do you do this problem? I always start off with this. This is the thing that gets me going, and that's what started me off in problem number 5. So to find the kernel, you set this linear transformation equal to the 0 vector of M2, which would be 0, 0, 0, 0. So most of your homework problems, if you're like, I don't know what to do, just set the linear transformation equal to 0, 0, 0, 0, and then let it flow. You're like, no, that doesn't sound good. Okay, well, let's just do this. So this is A minus C. That's the first one, equals 0. That's kind of like your E11 position there. So that's good. So the next one I should do is the E12, which is A plus B equals 0. And then what is this? B minus D equals 0. And the last one is A plus D equals 0. Now if you're thinking, wow, Joe, this is so different from the last problem. Look at your last problem. What was like one of the first things we did? We said this thing, and I'll put it over here even though it seems like I'm cheating on this. We set it equal to 0, and then we set those guys equal to 0 and got this, and then jumped to a matrix. So I'm just trying to show you that we're doing the same thing. Now the matrix I'm going to jump to here, I'm not going to write the 0 column because I'm actually looking for this matrix right here. So this matrix looks like this. 1, 0, negative 1, 0. Okay. And I'm not going to put the equal in the 0. And then the next one's 1, 1. And then C and D are 0, so 0, 0. This one is 0, because the A is not there. 1, 0, negative 1. And then the last one is 1, 0, 0, 1. 1, 0, 0, 1. Now let's just double check this and see what we have here. This A minus C came from this first row, first column, which kind of is going to represent the E11. And then A plus B, that's that one. So this is sort of the E12. And then this one is E21, and then this row is E22. And now look at the columns. These columns, well, where are these coming from? This is A, B, C, D. Okay, so that's what they are, aren't they? But look what A kind of corresponds to the one element, A times 1. And then B times X, I'll just put the X there. C times X squared. And D times X cubed. So look at what we have here. That's your ordered basis B. 1, X, X squared, X cubed. It's an ordered basis for P3. And then coming down the rows, E11, E12, E21, E22. That's your ordered basis for M2. This is 4 going into 4, and your matrix is 4 by 4. So those 4's got swapped, but we didn't see it. This right here is your matrix. This is your matrix that we're looking for, the matrix of T relative to the ordered bases B and C. And so we can label it below. Here it is. I'll just go like this. Okay, what are we trying to find on this matrix? We're trying to find null space and call space, because then we can translate it to what? Kernel and range. And then once we find those, it's all downhill. But before we find those, I'm just going to reduce this matrix. I'm not going to show you all the pain that I went through to do this. 1, 0, negative 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, and then the last row was all zeros when I finished it all. Now if you want, you could still write these guys, you know, along the rows and columns, but I'm going to go ahead and say this is A, B, C, D, because that's going to help me. Those are going to be the letters. And what am I trying to find on this matrix? I'm actually trying to find the null space. So those are zeros. I am going to need another piece of paper. This lecture is so long, it's burning up paper and camera batteries. It's bad. It's good because it's got a lot of good things in this lecture, but it's just a lot of stuff. Okay, so let's go ahead and label these guys. I'm going to go ahead, box all my leading ones, identify those variables as bound. Bound, 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 and then that one is free. So D is free, D is T. Sounds like we're doing poetry here. C, so remember, this is an equation that says C plus D equals 0. So C is going to equal negative T. B plus C equals 0. B is going to equal negative C, so B is going to equal T. Tell me this isn't confusing. And then what do we have here? We have A minus C equals 0. So that's like A plus T equals 0. A is going to equal negative T. So it looks like this. Negative T, T, negative T, T. When I splactor, which really isn't much splitting, I have T times negative 1, 1, negative 1, 1. So I have that right there. The null space, that is what I'm trying to find. The null space, and even though the matrix is called that right there, you know, the matrix of T relative to those ordered bases, I'm just going to say null space of A. And it happens to be the span of how many vectors? Of just one vector. -1, 1. -1, 1. Now, is that the kernel? And the answer is no, because the kernel comes from P3. The kernel must be the span of polynomials from P3. But take a look at this. If this is supposed to be from P3, look at, here's the order right here. I mean, we have the A, B, C, D, which corresponds to the 1x, x squared, x cubed. I'll put it right above this. This is 1x, x squared, x cubed. So now we can jump right to the kernel. We can say the kernel of your transformation equals the span of, okay, this is one element in the null space. So there's only going to be one element, one polynomial right here, and it's going to be -1 plus x minus x squared plus x cubed. So there's the kernel. Any linear combination of that, which is just scalar multiple of that, when put into this linear transformation, will yield the zero vector, the zero matrix. So let's just check it out. Like if A is -1, and okay, so what do we have here? That would be -1 minus a -1 is 0. A plus B, that would be 0. B minus D, which is 1 minus 1, 0, and A plus D, 0. So I've just checked it with the value. A is -1, B is 1, C is -1, D is 1. But you can do any multiple of this polynomial, and it would still zero out when shoved through the linear transformation. What is the dimension of the kernel? The dimension is 1. Don't say 4, there's 4 terms there, but it's 1 vector. And it will always be the dimension of the null space of your matrix of T relative to the ordered bases. Since the kernel has dimension 1, that tells us that this linear transformation is not 1-to-1. Okay, let's go ahead and find the range. Now we might already know something here. By the general rank-nullity theorem, we know that the dimension of the kernel, which is 1, plus the dimension of the range, which we don't know what it is, has to equal 4. So we know from the general rank-nullity theorem that 1 plus question mark equals 4, 1 plus 3. So 3 is going to be the dimension of the range. To find the range, I'm going to find the call space of A. Okay, so we come back over here, put that under there, and here is A. We're trying to find the call space. It's going to be, we go over here, we look at our leading ones, there's 3 leading ones, and we're not surprised because we already knew that there was going to be dimension 3, and we take the 3 original columns. So I'm going to write those down. This is going to be the span of that basis. The first one being 1, 1, 0, 1. The second one being 0, 1, 1, 0. The third one being -1, 0, 0, 0. Now that's not my answer, and that is not the range, but it's going to help me get the range. And notice, look at this. This is 1, 1, 0, 1. It's like 1 times E1, 1 times E11, 1 times E12, 0 times E21, and 1 times E22. That is what this represents. So this is E11, E12, E21, E22. So when I'm translating the call space to the range of the linear transformation, I'm going to say the span of 3 vectors. Those 3 vectors aren't going to be R4, they're going to be the 3 vectors in M2, which correspond, and this is going to help me get it. So the first one will be this 2x2 matrix that says 1, 1, 0, 1. The next matrix will say 0, 1, 1, 0, and in an earlier lecture I identified that as the evil identity, which you will not find in any linear algebra books, but it just looks evil to me. It looks like he does weird things when you multiply him by a 2 by 2 matrix. And then this last one's going to be -1, 0, 0, 0. Now, that might bug some people, like put that in their basis and they'd rather have 1, 0, 0, 0. There's nothing wrong with scaling any of these things down if you don't like that, but I'm going to keep it this way. I used to scale things down when I first taught the class, and then I would like lose half the class. Like, why did you do that? Why are you scaling down the matrices? And I'm like, because I can, and then that even made it worse. So I just keep things the way they are, and then maybe tell you verbally you could write this answer and just have this, and then just have U11 then. So we knew the dimension of the range was going to be 3. Well, here it is. It's been verified. And the range, does that equal the codomain? Does it equal M2? This does not equal M2. Therefore, this linear transformation is not onto. Okay, so let's see if we answered all the questions. Did we find our matrix of T relative to the ordered bases B and C? Yes, we did. Did we find the kernel and the range? Yeah. And their dimensions? Yeah. Did we do the? Yeah. The rank-nullity theorem, the general rank-nullity theorem, let's just do that really quickly. 1 plus 3 equals 4. 1 plus 3 equals 4. Okay, this sounds kind of dumb, but here goes. This one is the dimension of the kernel. Trying to color code it consistently. Oh yeah, okay, so the next one is this color here. That is the dimension of the range, and then this weird kind of green color, 4, that is the dimension of, what is it? Is it this 4 or that 4? This is very important. It happens to be the dimension of the domain. Okay? So that's the general rank-nullity theorem. We're almost done. Look at this. T inverse. Well, the inverse linear transformation exists if and only if your linear transformation, which is this guy right here, is both 1-to-1 and onto. And it's not. So what are we going to say about T inverse? T inverse does not exist. And if it did exist, and I don't think you get anything this hard in your homework, but if it did exist, then this 4x4 matrix would be row equivalent to the identity, and to find the inverse transformation, so you're not going to get anything this bad in your homework where you're working with this, you would have to find the inverse of that 4x4 matrix, and then that would sort of point you in the direction of writing down the inverse transformation. But this one does not exist, so we don't have to worry about that. So this completes section 6.3 with a little 6.4 and a little 6.5 thrown in there. I will still officially do a little more from 6.4 and 6.5. This was a long video, and if you made it this far and you're still awake, oh, that's amazing. You guys have a good day, do your homework, I'll see you in the next video.